We'll go ahead and get started again here. As you all know, the Barry Arm Landslide's been in the news for about 2 years now, it seems like. And so we're thrilled to have Dennis Staley come and talk to us. Dennis is a research physical scientist at the U.S. Geological Survey Alaska Volcano Observatory in Anchorage, where he leads a project related to landslide hazards in Prince William Sound. And we're hoping to learn how much more about the landslide. So welcome, Dennis.
Great. Thank you very much. And thanks for extending the invitation to present here today. I've moved to Alaska last fall and have been fortunate enough to spend some time out in Prince William Sound and all the seasons since and at all different elevation bands. And it's really, truly a special place. So I appreciate all the efforts people within this room do towards Prince William Sound and stewardship. So let's see. Guess we're over here for my slides. Dennis Staley, a research scientist at the Alaska Volcano Observatory. And I'm going to be presenting today about tsunamigenic landslide hazards in Prince William Sound. Much of the talk will focus around Barry Arm, given the high visibility of it and our recent efforts that are being directed towards that individual landslide. But we are considering landslides across the region itself. I'll be presenting today on behalf of many, many others. And just to give you a kind of quick rundown just of our science partners, these are the agencies that we work with directly on the science issues. State of Alaska, the Division of Geological and Geophysical Surveys, I'll shorthand them as DGGS, USGS, the large team of us in the Landslide Hazards Program, and the Alaska Volcano Observatory. NOAA, we work with the National Tsunami Warning Center. I'll shorthand them as NTWC, and the National Weather Service. U.S. Forest Service, as many of you in the room, a few familiar faces. Alaska Volcano Observatory, which I'm now a part of as of last year, and the University of Alaska Fairbanks Alaska Earthquake Center are also partners of ours. I will refer to them as AEC. So coastal Alaskans are certainly no strangers to tsunamigenic landslides. Probably the most famous example was in 1958 during a magnitude 7.8 earthquake in Lituya Bay. And what happened here is that if you look in the sort of back left along the mountain front, there's a landslide. About 30 million cubic meters failed directly into the water, caused a huge wave. Highest recorded run-up in history, so about 1,700 feet on the opposite valley wall. It spilled over into the main part of the bay where there were 3 different vessels. 2 of them, unfortunately, did not make it through the event. There were 5 fatalities, but there was one ship that actually rode it out. And so the wave traveled all the way out, the full 11 kilometers to the edge of the bay and into the ocean. And the wave itself resonated for a period of 20 to 30 minutes, I believe. So kind of a prolonged event. Back in 1964, we're all familiar with the magnitude 9.2 Great Alaskan Earthquake. Here, it's been postulated that perhaps 2/3 of the deaths in Prince William Sound could be related potentially to near-shore submarine landsliding during that earthquake. So if you look at the black dots on the map there, you'll see 14 or so that have been identified by my colleague Peter Heusler at the USGS Alaska Science Center. And these are a pretty important feature and a really important hazard for landslides in Prince William Sound, and one that's pretty difficult to characterize given the fact that they're underwater and they're typically triggered during large shaking events. Another more recent example was back in 2015, and I believe it was October of 2015, in Taan Fjord, or Icy Bay, where there was a 60 million cubic meter landslide just to the southwest of the Tyndall Glacier that failed into the water, basically displaced all the water at the fjord head and caused a wave with run up approximating 200 meters just to the right where it kind of runs up. You can see in the map on the right hand side where it runs up on the shore. Big long run out of that well into the fjord. The wave itself propagated out into the main part of Icy Bay, and I believe there was about an 11-meter high wave on the opposite side of the valley. So we're all familiar with the Barry Arm landslide, everybody in this room, I'm sure. And this is going to be the focus of most of what I'm going to talk about for the remainder of today. So back in 2019, a local resident artist kind of thought that the slope up there looked a little bit fishy and a little bit suspect. So that information was conveyed to a couple of scientists, relatives and friends, and we identified that there was a very large potential instability in Barry Arm. That's the magenta diamond in the upper left-hand corner of the map. About a year later, in May of 2020, the group of concerned scientists wrote an open letter that attracted a great deal of attention in the media and at the federal level. So I've probably all seen the headlines in the Washington Post, New York Times, all the bigger media outlets. This landslide's about 50 kilometers, I think, straight line distance from here in Whittier, and a wave that was generated at the Barry Arm landslide could potentially cause all kinds of problems, particularly in western Port Wells. So to give you an overview of what the landslide looks like, we've been looking back through a historical catalog of aerial and oblique imagery to see kind of what the history of that landslide is. There's a picture on the left from Bradford Washburn taken in 1937. It was June 1937. And another picture on the right from our USGS Alaska Science Center director, Chris Zimmerman, on his flight in 2020. The landslide itself is a little over 3 kilometers long, so south to north, about 700 meters high. And we can see it going back into imagery, we think into the teens. There's an image from 1909 that's available that it's a pretty fuzzy image. So we're trying to track down the actual original source of that image to see if the publication itself may be degraded the quality. And hopefully we'll be able to tell if that landslide did exist back in 1909. But the fact that it is there does imply some degree of stability over time, since it did actually, in fact, survive the 1964 earthquake and a few other earthquakes since. But this doesn't mean the landslide isn't active and isn't moving. Going back, looking at satellite data, we were able to determine that the landslide itself, kind of the background rate was about 1.3 meters per year. There was a period from 2008 to about 2013 where it accelerated pretty quickly, so about 26 meters per year. That slowed down to about 10 meters per year from 2013, 2014-ish. And then finally, we're approaching that background rate of about 1.3 meters per year right now. But there is signs of activity. The landslide is a landslide, so it moves around, and it does exhibit evidence of things that could be concerning. So to put the Barry Arm landslide in the context of a few that we've already talked about, again, Lituya Bay, that's about 40, apologies for the mixed units here. I grabbed this from the open letter. So 40 million cubic yards for Lituya Bay. Greenock Lake, that's one that fell into the lake and it's outside of today's discussion. Taan Fjord, about 80 million cubic yards. And then Barry Arm landslide, 650 million cubic yards. So we're looking at a landslide that's it's quite a bit bigger, 10-ish times the size of Lituya Bay, which you can see what the near field hazard was for a landslide in that area. So back in 2021, sorry about all the text, but I promise there's only 2 slides with a lot of text on it. So back in 2021, the U.S. Congress authorized the USGS Landslide Hazards Program to address concerns about the potential for landslides in Prince William Sound. We were directed to conduct data collection and analysis to develop a site-specific landslide hazard assessment, provide recommendations to support a long-term monitoring strategy, and then work with our partner agencies to develop an early warning system to alert of an impending or actual landslide that could result in tsunami. So for the focus of this talk, I'm going to keep this in the context of the development of an early warning system, because I hope I can articulate why the first 2 bullet points actually are just a part a smaller part of the bigger picture of the early warning system development. So the United Nations Office for Disaster Risk Reduction back in 2016 defined what an early warning system was. I believe this has been updated since, but the definition has remained the same. So an early warning system isn't simply just putting instruments in the ground and then having a button with a siren attached to it. It's a lot more than that. So it's an integrated system of hazard monitoring, forecasting and prediction, disaster risk assessment, and then communication and preparedness activities, systems, and processes that enable individuals, communities, governments, businesses, and others to take timely action to reduce disaster risks in advance of hazardous events. So kind of a mouthful, but there's a few really important pieces here. And first, I'm going to focus on this timely action to reduce disaster risks and see what that means for a landslide, such as what we have out in Barry Arm. So what does timely action mean? I think we need to understand the nature of the timing of the landslide and where the risk is relative to that timing. So if you're in the near field, I do have a laser pointer that I'll use. I guess it doesn't work on televisions. So that's the Barry Arm landslide off to the right. We're looking down and back towards Port Wells and Harriman Fjord. So in the near field, basically the hazard arrives instantaneously. We're looking at wave heights well in excess of 50 meters in Barry Arm, run up on the order of Lituya base scale, run up on the opposite side of the fjord, so somewhere around 1,500 feet, and a very quick arrival. So there's just, the landslide will fail, the water will get displaced, and there'll be a massive wave right in Barry Arm. Once we get a little bit further out, so right where that magenta dot is on the map, shows you a approximate location of the terminal moraine, where you have the intersection of Barry Arm, College Fjord, and Port Wells. And at that location, it's approximately 10 minutes that it'll take for the wave to arrive there, based on some modeling. Our wave heights are quite a bit smaller, especially once you get on the south side of that terminal moraine, so somewhere a little bit over 2 meters. Once you get down to Western Wells Passage, it's about 15 minutes or so, a little under 1.5 meters maximum wave height from our worst case scenario. And then finally, once we arrive here in Whittier, it's about 25 minutes for the wave to arrive. And a couple hundred meters offshore, just behind us here, it's predicted that the maximum wave height would be a little bit over 2 meters based on our modeling at the USGS. Katie Barnhart, all of these data are summarized from Katie Barnhart's 2021 open file report. And why is this important? Well, if we get back to early warning and timely action, the Alaska Earthquake Center published a map showing evacuation times in Whittier for pedestrian traffic. And so the scale on the left, it's 0 to 3 minutes is the darkest shade of blue. And then I believe it's 28 to 30 minutes on the red color all the way to the right. And if you see, there's certain places that we'll want to draw attention to where we're in the oranges and reds. And so those are the areas where, even if everything went perfectly with the detection of a landslide and the issuance of a warning, we have some issues in terms of the time it takes people to travel by foot out of those locations in red and orange. So getting back to our integrated system of all these different pieces, we'll start stepping through each one of these to see how the USGS and all of our partners in both the state, federal governments, local communities, and in academia and private industry are working to address this. So we'll start off with the hazard monitoring, forecasting, and prediction. And this is sort of one of the main roles that the USGS is playing at this point in time. So out in Barry Arm, we have a number of different types of instrumentation set up. There's actually new stuff going in the field today, where we're going to be redeploying a ground-based radar that was set up all last year to measure landslide deformation at very high spatiotemporal resolutions. So I'll be leaving here directly to go help with that installation. But we have a variety of equipment out there. We have geophysical monitoring. There's a seismometer. There's an infrasound that's going to be put in that those are used to detect not only the occurrence of the landslide. So should the landslide fail, there'd be a large sound wave that was issued. There'd be a series of seismic waves that would be issued. That would be quite obvious if you were watching those data in real time. But also the geophysical data can be used to monitor what could potentially be indicative of precursors to landslide motion. And so here's where you may see rumbling in the seismic data, or noises associated with rockfall or other types of smaller mass movements on the landslide that could suggest a precursor. Now, the science is still largely in its infancy for doing this type of work, but we've got a really solid team of researchers and operational folks working on that problem today. So we not only the geophysical monitoring do we have in Barry Arm, we also have environmental monitoring, where we're doing taking measurements of meteorological conditions that could potentially trigger a landslide or elevate the susceptibility of that slope to failure. Things like prolonged rainfall, things like rapid increases in temperature, both above the surface and below the surface, that could introduce a large amount of water into the landslide mass itself, thereby destabilizing the slope. We're also, like I said, using that ground-based radar to monitor landslide deformation. With that radar, we can, in theory, detect deformation at about a centimeter scale across a wide swath of the landslide itself. The temporal resolution, the antenna itself goes back and forth every 5 minutes. So you can compare the radar image from 5 minutes ago, from an hour ago, from a week ago, to get some sense of how that landslide is moving over time, when it's moving, and what potentially the environmental conditions were when it moved, and if you're seeing any signs of that movement at the seismic array or the infrasound. So this is just an example of kind of our workflow when we're trying to analyze some of these data. So if you look close pretty much under the blue triangle at the upper left side of the screen, you'll see a rockfall scar. So this is not something that's uncommon at the Barry Arm landslide. There's lots of rockfall activity. There's steep slopes, there's debris flows, there's small landslides. This is just normal behavior for a large active landslide complex. But we did identify that in the imagery. It was in early October of last year. We were able to go back and take a look at the seismic data that were being collected at that site. It wasn't a huge seismic signal, but landslides and rockfalls do have a pretty distinctive wave form in the seismic array. And that's what that looks like. So we can pretty precisely time the actual timing of that event very, very, very accurately because of the seismic signal that we see in the data. So you can see the spike about the middle of your screen. And unfortunately, the font's too small and my memory isn't good enough to remember exactly when that occurred. But we can step through this and not only detect larger events using real-time analysis of these data, but we can get a sense of the frequency of rockfalls and some idea of the potential triggering mechanisms for those. To supplement this effort are the National Tsunami Warning Center tide sensors that are deployed out there. You can see little blue squares, one on Point Duran, which is on the south side of Barry Arm, and then two other ones, one at, they're calling the North Shore site, which is about halfway between the Barry Arm Fjord and Point Pakenham, which is the southernmost point on the right-hand side or east side. If you squint, you can probably make out the solar panel, at least for the tide sensor on the right, and that's simply a power source for a water level sensor that's deployed in the water. Then that can measure the pressure of a wave as it passes over. So they use it for not only measuring tide, but you can look at if there's smaller events like glacial calving, you can actually see that signal of the wave that passes from even small events and use that to help better inform models of wave propagation in Prince William Sound and Barry Arm and Port Wells. So it's multiple levels of analysis that can be done in addition to real-time detection of a large event. So getting back to our definition of warning a warning system is disaster risk assessment. And again, this is another part of what we've been focused on here in the past year at the USGS. So the very first thing we need to do is figure out, well, we know about the Barry Arm landslide, but are there other landslides that we need to know about that are in Prince William Sound? And yes, there are. And the more closely you look, the more you're going to find. So this map doesn't necessarily indicate any sense of hazard or risk. It's not intended to convey that. But these are locations where there either is evidence of an existing instability, so a landslide that maybe hasn't failed yet, but has cracks or scarps or faults that could suggest movement, or landslides that have already failed catastrophically, and we have a good idea of when they may have happened. So you can see there's a bunch of red dots on the map. Off to the right-hand side, you can see there's a large instability that's just above the terminus of the Columbia Glacier, and another, I believe that's in just up here above town. Probably wouldn't run into the water, but it could be problematic should it exhibit evidence of increased movement. And that's not to be alarming. We're going to take a very, very close look at satellite data to see, is there evidence of active deformation? Are there morphological features on the ground that could suggest this thing is actually unstable and getting worse or more susceptible to failure? And then if it should fail, what is the likely failure mechanism? Is it going to just kind of fall in little pieces, or is it going to go all at once? These are the types of questions we're attempting to answer. But the first step in doing that is just figuring out where are the existing landslides. Geology matters when it comes to landslides. So there's at the scale of the landslide itself, there are certain structures that control how the stability of the mass itself. The mineralogy matters, that helps determine whether it's going to fail catastrophically and how far it would run out. The lithology itself may also be indicative of broader scale regional differences that could explain why we see landslides in certain places and not others. And from that, we can make a determination. Well, we don't really have to worry over in this part of the sound because the geology isn't necessarily conducive to the initiation of landslides. So we've got a team went out last summer and mapped about 40 sites and are aiming to do about the same this summer, same number of sites. So we're looking at the nature and geometry of discontinuities in the rock that could control stability, the material properties, all the different things that could potentially affect both local and regional stability and susceptibility to landsliding. We've already gone over this slide, but the part of the hazard assessment is to look at wave travel times and heights and determine what locations might be at risk, not only for Barry Arm, but other landslides in the sound and other locations in the sound beyond what we're showing here in Whittier. Katie Barnhart also recently published this science-based data release that shows a map of inundation and run-up, so a very site-specific assessment of where the hazard is on shore that we can then go back and inform some risk analysis. And the intention is to do this for other locations as well. And then finally, our communication and preparedness activities, systems, and processes. This is where the rubber really meets the road. This is how the public knows what's going on. And so we're heavily reliant at this point upon our partners here. So DGGS has a website that they update every couple weeks. There's a mail list you can get on that will give updates with any sort of discovery that we find at the Barry Arm Landslide that could be relevant for hazard and risk characterization, inform you all of field work that we're doing, those types of things. And then finally, probably our biggest partner when it comes to the communication of preparedness activities is the National Tsunami Warning Center. And so we're working with them to develop their capabilities for monitoring, detection, and warning of these non-seismic source tsunamis. And so they're at tsunami.gov will be the primary source for information should there be an event. So I'll leave it at that. Some relevant citations for those that can actually make it out on the screen. My contact information is off to the left. There's a number of you in the audience today that I'd really like to talk to about potential outreach opportunities, ways that we can better engage with the community. But unfortunately, I have to run to the airstrip to catch transport out to Barry Arm here as soon as my talk's over. So if you are interested in speaking with me about outreach, community engagement, those types of activities, please shoot me an email and I'll get in touch with you once I get back from the field at the end of this week. So with that, I think there might be a couple minutes for a question.
Yes, I've spent a lot of time up in that area, and on Cox Glacier, on the right-hand side, to my knowledge, there's a very large landslide, and you can see how it was stopped by the glacier that it hit. Yep. So is that a pretty big slide?
Yeah, I mean, if any other place, I think that would be a major attention grabber. Given the scale of some of the other landslides in there, it's a big landslide. It's one we keep track of, but it's hazard for anybody that might be on that beach. But I don't see it being a significant like downstream hazard. Yeah. I know that the landslide, if we're thinking of the same one, there's a landslide right up above the Cox Glacier fan. And I believe it was the failure of that and subsequent damming of the stream channel that ended up making that beach not quite as fun for camping on, because there's a large number of big clasts on it now. I think that kind of periodically does that and spits out material onto that fan. Yep. So review raw materials, more land below for animals and plants to live. Forest fires have purposes of regrowth. Are landslides similar for land? Okay, so I think this is a question about the disturbance of the land from a landslide and what that means for like recovery. So here, if you have a fire, you may have succession after the fire and a different opportunity, different type of ecosystem, different boundary conditions for those animals living on the land. Are landslides similar? I think over time it does introduce some different topography that may be suitable habitat for different vegetation, different animals out there. It's certainly not my expertise, but I guess the immediate concern that I would have is just when a landslide fails, there's potential follow-up instabilities and landslides that could be an issue. So it may be an active land surface for quite a number of years that may not be conducive for the establishment of long-term new vegetation or habitat for animals.
I have a question.
Yeah.
Which is, I know you probably can't answer this, but I just had someone text me and said, should they go up there? And I know you can't, not probably position to do probability, but any thoughts on that? How would you answer that?
Yeah, we're certainly not in a position to do probability. And I think, with especially people that live in Alaska, I think we're all familiar with risk just in our day-to-day lives. And so what I would encourage people is just to know that it's a very risky place to be. It's hard to say if that's going to fail tomorrow, if it's going to fail next year, if it's going to fail in 10 years. But should it fail, it's a very dangerous place to be should that fail. So I think we're going to do our best to give public insight into whether or not that is moving, whether or not the hazard is elevated. And I would encourage people to be aware of that hazard and make their own informed decision on that risk. I personally wouldn't be going up there if it wasn't for work.
Thanks.
So if Barry Arm failed today, would we receive a tsunami warning alert if we're in sound or in a
The National Tsunami Warning Center is. Oh, I'm sorry. If the Barry Arm landslide were to fail, would there be a warning received today? That's the National Tsunami Warning Center is working to develop an operational capability. Dave Snyder will fortunately be talking later today and probably can address that question better than I can.
More? We have one question coming in from Corinne Smith online. She's wondering, early on, 2 videos were released that predicted worst case wave height and currents. Do the updated forecasts include currents?
The updated forecasts do not yet include currents. The modeling we do does include that as an output, but I don't think those are as numerically stable as we'd like them to be for planning and emergency management purposes. So we're puzzling through the best way to get that information better characterized.
Any other questions? All right. Thanks, Dennis.
Okay, thank you.
All right, that was Dennis Staley with the USGS Alaska Volcano Observatory talking about the landslide risks and warning systems in Prince William Sound. So we have another break here till 10:30. And again, coffee, tea on the side for those online. Sorry, you have to go get your own. And there are some snacks in the back. The back room, there's some snacks also if you help yourself to that.